Okay, I'm going to talk a little bit about feedback in machine learning. And I'll start by talking about why we care about this. So it's becoming more and more important. It's been kind of a democratization of machine learning recently, which is wonderful. We've seen it being applied in all kinds of different domains, and it's making a huge impact. But why do we do it? Well, the main reason we do it is because we're interested in either building a module of some typically larger system which has higher performance than we're able to achieve by hand engineering it, or we believe we can do it much faster. So by taking advantage of data we can generate, we can build something much faster than we can hand program some behavior, right? And so Mike talked about an example. Pedestrian detection is one very natural example where the state-of-the-art methods effectively are all data-driven in some fashion. And that's not for lack of trying. People have tried methods that are much less data-driven, but they haven't had great success. But as I said, the democratization of machine learning has meant that there are limitations and subtleties of these techniques. Mike talked about some. I'm going to talk about another subtlety that comes up quite a bit, and that is the use of feedback. So when I say feedback in this context, what I mean is that we have some machine learning component of a larger system, and I'll give you a caricature of such a system in a moment, that its output in some way filters back and becomes part of its input. Okay? That's what I mean by feedback in this particular context. Okay, so I have a total toy sketch of a system that might occur in, say, a flight control system. So there's all kinds of boxes, and all these boxes are connected, and this is a manually engineered system. So people have designed a whole series of, for instance, software modules that connect to one another in some complicated, typically data flow style architecture, but usually there's also internal state. Okay? And inside that, someone has decided it's really important to do wind speed estimation, and they're having a hard time doing it in a purely engineered way, so they want to do it in a data-driven way. Maybe it's wind speed, maybe it's wind direction, depending on what you're particularly interested in. And how does an engineer go about doing something with this in a machine learning way? Well, here's my, again, character sketch. The problem you want to solve is wind speed estimation, and you instrument the code so that it's able to dump out effectively its inputs as a vector. So the kind of picture over here, it dumps out an input vector, which is the inputs to that module, or transformations in the input to that module, and then through either automatic methods or manual methods, a target output. This is what we want the system to output, right? The wind is coming from the north, okay? For instance. Then what happens is those things get dumped out as vectors, they get put in some data store, so think of that as they're being put out as CSV files stored on a disk, and then it goes off to your favorite machine learning algorithm, be that TensorFlow or libsvm or SparkML, something, or maybe some internally generated thing. And the result is a new version of the wind speed estimator, okay? Or parameters for that, if you prefer to think about it that way. That's kind of the typical model. And we've gotten very good, I think, at people understanding the statistics of what they should be checking. So they should be making things like ROC curves or PR curves and looking at their performance. And again, we always emphasize you want to do that on test data that's held out from your training data, and you can look at your performance. Okay? The problem one finds in practice is that this is often actually irrelevant, and in fact, you will get results that don't match this performance when you use it in an actual system. Okay, so the PR curve that one generates, people often find the performance of the system when you use it in situ is very different than the performance that you get at the PR curve. Why would this happen? Right? Well, the title of the talk might tell you. But let's take a really extreme example so you can understand what could happen. Okay, so we go build a wind speed estimator through great pain and work and lots of machine learning effort and lots of engineering effort, and it gets 99% accuracy. I don't know, maybe it's in discrete bins. It's 0 to 5 miles an hour, 5 to 10, 10 to 15, so on and so forth. And it's awesome, right? We really nailed it. Problem's great. Okay, but someone thinks it'd be a really great idea if one of the features of that wind speed estimator was the wind speed estimate from the last time step. Right? Because then you could get kind of a smooth estimate of the wind speeds, very, very natural thing one would want to do. It could happen deliberately, or much more likely it happens accidentally. The output of that system goes through some other series of modules and ends up back through something which doesn't even have that name anymore. It's just an input to the system. Okay, so the next time we go build a classifier, we're going to dump out that training set. In that training set is a feature which is actually the output of the last classifier we trained. Right? Again, maybe through some indirection, but it's there nevertheless. All right, the intern comes in, and he says, wow, I can build a classifier it's not quite as good. It's 98.5% accurate, but it's 1,000 times faster. In fact, it only branches on one feature, it turns out, interestingly. Okay? Team rejoices, goes out for beers, intern's super happy, installs the classifier in system, and it completely and totally fails when you run in the system. Why? It just predicts the last output. So it just predicts the same thing again and again and again and again. Okay, total and utter failure. Now, it's usually not this catastrophic, but a subtle version of this happens all the time. There's some variant of this where the performance on that test data that's held out is nothing like the performance of the system in situ. Okay? So what I found is, although this sounds like this is a toy example I just cooked up, this is actually totally ubiquitous. I've never worked on a large engineered system where the machine learning components didn't have this property. Okay? So sometimes it's very indirect. It's actually through the feedback with the environment. Right? So for instance, in the example that Mike Wagner just gave, right, there is a feedback loop in any pedestrian detection system. If it in any way directs the behavior of the vehicle, right, you are getting a different set of images than you would have gotten had it not directed the vehicle. Maybe too subtle to matter in that case, but there is a feedback loop through the environment. Okay, so these feedback loops are ubiquitous. They're largely unrecognized, so this is not something that you hear a lot in most industries. You do hear it, for instance, from folks at, for instance, Microsoft and Google. They talk about these effects on things like web search, right? So the predictions you make affect what you do, okay? It's potentially disastrous in the obvious way I just said, that you can get kind of catastrophic performance failures, and you actually have no idea what the performance of your system is, right? So you have this held out data and you make your beautiful PR curve, but that PR curve has nothing to do with what the system does, right? It also is this funny property that people, I don't think, realize from a V&V point of view, which is you can't actually recreate that classifier anymore. If you lose your classifiers, you have no way to create that because the classifier you built today is actually dependent on the time history of all classifiers you've ever built, right? Because it's developed from that time sequence. So for instance, people don't think about necessarily keeping those around as critical artifacts, but they're actually critical artifacts if you ever want to recreate your system, right? So this has been recognized by some folks. There's a nice paper by the Google team talking about a variety of things. One of these is feedback. It's a great article. I would encourage everyone to read it. I actually disagree with their diagnosis of what to do with feedback. In fact, they say you should go run a bunch of bandit algorithms, which I think one should not do in this particular case. And I'll take you through how I think you should view the problem. Okay? So the first point I would make is that you have to at least know this is happening to you, right? And be able to control it. So first, understand feedback loops in any system with learning. You can detect them, so you can basically dump out what the feature vectors I showed you before, and then you can deterministically rerun the system and make sure that you're getting the same input vectors that you got before, right? So if you change that module, if you don't have a feedback loop, you should get the same inputs no matter how you change that particular module in the system. So that's a reasonable sanity check. If that's not happening, you must have a feedback loop somehow. Okay? And I want to point out, this can happen completely without you knowing it, right? So you're working on some large code base, someone somewhere in your organization introduces a diff which makes some feature that you're depending on depend on your output. And you would never know it unless you were actually instrumenting it, right? You may not be able to control this on your own as a machine learning person. So you have to at least have some way to control it, meaning instrument your code so that you can detect it. Then always measure your performance of the algorithm in system. The result of your performance on held out test data, like a test file that you've dumped out, is irrelevant. All that really matters is if you measure performance on that set of labels in system. That's the thing that matters. The other point is actually irrelevant and may mislead you. You may think you're doing much better than you actually are. And ensure the ability to recreate each learn module in the system. These are kind of the minimum bar requirements. So it better be possible to recreate that thing. By the way, it's not that unusual for even mature organizations to run into a situation where they are unable to build the classifier that they built before for various reasons, this being one of them. But then embrace feedback. Actually, feedback is a really useful thing if you know about it and control it. So as I said, for the wind speed estimation case, it is nice to have a kind of smoothing effect where you take advantage of previous predictions, right? For lots of learning control applications, you have that same property. This is becoming more and more important. You see lots of work now in, for instance, the neural network community or the natural language processing community where they build recurrent predictors that are, in fact, consuming their own outputs, right? And again, if you're aware of it, it's a very sensible thing to do. The key to do this, or my view of the key to view this, is to view as we are moving from a supervised learning setting to an imitation learning setting. And let me take you through that. and give you a concrete example. What do I mean by imitation learning? So this is a phrase commonly used in robotics, and it's trying to learn some behavior of a system from demonstration by a human. Okay, and you're going to ask, what is the demonstrator here? I'm going to take you through that. And the key thing to notice is when you want to learn behavior, supervised learning is not the same as demonstration learning. And the real key is that when one thinks about imitation learning, fundamentally decisions have consequences. When a machine learning algorithm outputs something, that affects ultimately what it's going to see at the next step. In some sense, that is the only case we care about machine learning, right? If it doesn't actually have an effect on the world and ultimately its own inputs, why would I care to even use it? Okay. So, of course, the classic instance of this was Dean Pomerlew's work on driving across the United States, based on a neural network looking at a camera image, and learned by watching him steer the vehicle. And he actually talks about this problem, this feedback problem I'm describing in some detail. It's an excellent paper for those who haven't read it. And I'm just going to walk you through very quickly an example, a toy example of this, done by one of my grad students, where we're going to look at a machine learning problem and how you can fix this problem I described. So input is going to be camera images, output is going to be steering angle, as done by Stefan Ross, former graduate student of mine. The supervised learning approach says you collect a bunch of expert trajectories, you get input images, output steering angles, you make a big data set, you train your favorite predictor, in this case linear regression, and you output a learned policy. That's the kind of supervised learning approach, okay? And I will, in the interest of time, shortcut this video. Here's Stefan driving. Stefan, good driver. Too much time playing video games. Okay, here's the supervised learner doing the same thing. Questionable, not so good. Okay, doesn't work very well. So what goes wrong in this particular instance? Predictions affect the future inputs and observations, okay? And we have fundamentally broken the supervised learning assumption of independent and identically distributed data, okay? And the main problem in kind of understanding what's going on is we don't have the ability to recover from the mistakes we've made. So the learner makes some error, it now sees something atypical, driving, say, near the edge of the road, and it has no idea what to do because it never saw the human drive near the edge of the road. There's no way to recover from its own mistakes. Okay? Just like in the feedback loop I was describing before, the system has no way to recover from its own prediction mistakes. Okay? So the intuitive solution is interaction, and I'll very quickly take you through that, but the idea, there are many algorithms that you can apply to this problem. This is the simplest one, which is you do exactly the supervised learning thing. Now you execute the thing you just learned, and you correct it. So you continually have the human say, nope, that's not what you should have done. Nope, that's not what you should have done. Nope, that's not what you should have done. And then the inputs are generated by the algorithm you're running, and the outputs are generated by demonstration, by in this case, the human. You aggregate that data together, and you iterate this process. You're always running your current best predictor, and you're always correcting it by the human. Continuously aggregating that data together. Okay? And the nice part about these things is you can now actually prove rigorous things about them. You can prove that as long as you can do a good job of each of the kind of supervised learning tasks along the way, the system in situ will work pretty well. Okay? I'm going to spare you the video because it's really dull. If you do this, it just drives around in a circle. Okay? And just show you the plot. What the plot tells you is look at the black line and the blue line, and it's just telling you average falls per lap. If you train it in this iterative way, what happens is relatively quickly, the algorithm does pretty well and it stops falling. Okay? Supervised learning, no matter how much data you generate, which is human driving, and you're just collecting more and more of the human driving, it never gets better. It never learns to correct its own mistakes. And in fact, sometimes it gets worse. Okay, so how do we relate this to the problem of feedback in kind of standard predictors like the modules I described before? Feedback is a given in imitation learning. All imitation learning problems definitionally have feedback. Okay? So if we use these imitation learning approaches to apply to problems where we have a supervised learning problem, but there's actually feedback in it, then this problem actually goes away. And the way I want you to think about it is the learning module is the thing that is trying to imitate. The data, the target outputs, are the demonstrator. They're saying this is what you're supposed to be doing at this time step. You're supposed to be outputting this is the wind speed, this is the wind speed, this is the wind speed. The data is the demonstrator. The rest of the system, including feedback, is the environment the system is embedded in. And you run the same kind of iterative algorithms where they learn to correct their own mistakes. Okay? That's the kind of high-level take. So conclusion. Imitation learning is now widely used in a variety of different approaches. However, it's not as well known as it should be particularly for fixing these kind of systems. The methods are simple, practical, and widely used in areas like structured prediction, but not in safety-critical ML systems. And I think that's somewhere that they need to be understood and used. And high level, if you're building any ML system, you should know about feedback. You should always measure your performance in system in situ, as opposed to like on test data you've dumped out. And you should embrace imitation learning to improve performance. And that's it.